this button here so I know I'm ready. Okay, so find the worksheet that says Kelvin scale. It should have been right behind the notes. Okay, so Kelvin, Lord Kelvin, and you saw a picture of him. Now that's his given name by the monarchy of Great Britain. His official real name was William Thomson. But he did experiments with gases and realized that he needed a temperature scale that did not have negative numbers. Now, unfortunately, he did this after we already had Fahrenheit and Celsius. So we do have Fahrenheit, we do have Celsius. His is the newer scale, but for gas laws, like we've been doing this unit, his is the necessary scale. We need to use his necessary scale because his scale does not have negative numbers. That's super helpful to our gas laws to not have negative numbers. So with calculations, okay, the absolute zero has been determined by calculation. You saw we're getting close. You also saw we will never, ever, ever get to exactly absolute zero. It is impossible to isolate the heat out of stuff to get there. But by calculation, we know where that number is. Now, he was smart. He did us a favor. He made the sizes of his numbers on the Kelvin scale the same as the size on Celsius. So if this classroom warms up by 4 Celsius, it is also warmed up by 4 Kelvin. You see how easy that is? Okay. Now, did you know between Fahrenheit and Celsius, there's a 9 and a 5? It's weird. You have to multiply by 9 and divide by 5 sometimes, and other times multiply by 9 or 5 and divide by, it gets crazy. So he did us a favor, making it the same size. If this room goes up by 10 Celsius, it's gone up by 10 Kelvin. Nice and easy. So for gas laws, we're going to use the Kelvin scale because it never has negatives. So we will never calculate a negative for pressure or volume. That's why we must use our temperatures in Kelvin. Think about a box, just in your head, picture a box. Now picture I make this box smaller, 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 smaller. What's the most smallest I could ever make this box? 0, right? Would there be such a thing as a negative for the size of the box? No, it makes no sense. It would be impossible. There's just the math, no, it doesn't work. That's why we use the Kelvin scale, so we never get negatives for pressure and volume, because those don't exist. Now, on your paper, you have our formulas. Check them out. To get Kelvin, and again, I remind you, I hope you're putting your name on these notes and keeping them safe, because when we take our test over these in about 2 weeks from now, because we have some star testing next week. I'm not going to test you the week of star testing. That'd be bad. So in about 2 weeks from now, we're going to have a test, and then you'll have these equations for you to use. To get the Kelvin temperature, we take the Celsius temperature and we add 273. Now I know that seems like a random number to add, but that is the calculated number that makes the difference between Celsius and Kelvins. And then to get a Celsius, we can take the Kelvin and subtract 273, and that would be our Celsius. Now I want to point this out, put this down here. Again, Kelvins would never go negative. So if you get a negative Kelvin, you did something incorrectly. Celsius temperatures, we know, can be negative. We had some negatives this last February during that super fun, I say that sarcastically, during our super fun cold week here we had in February. We had some negative Celsius during that time. It was cold. As we saw in the video in Antarctica, it got really cold, negatives. Kelvins would never have a negative. So good idea you did something wrong if you get a negative for Kelvin. Okay, down at the bottom, we're going to practice a few of these. Some of you are already jumping ahead to them. That's awesome. Love that you're like, yeah, I get this. Let's do it. I'm given, on the left, I'm given Celsius. And this is typical. Normally, you're going to be given Celsius. So like when we do lab next week, we're going to be using thermometers at measuring Celsius. We don't have Kelvin thermometers. Almost no one has Kelvin thermometers. I don't know why. We'll use Celsius and convert to Kelvin. So if I have 37 degrees Celsius, how many Kelvins is that? 37 Celsius plus 273, because that was our conversion. We're going to take the Celsius, we're going to add 273. So what do we get there? 300 something, I'm sure. 310. Okay, sounds good. That sounds good. 100 degrees Celsius when I add 273. 373. So the human body, your body is 310 degrees, or sorry, there's no degrees, just 310 Kelvins. Water boils at 373 Kelvins. What about something super hot, something at 407 degrees Celsius? What would that be? 640. Okay, I was told 640. Let's go 680, yes. I bet I heard wrong there. 680 is I'm certain what you meant to say. I just heard wrong. But now we got negatives. What's that going to do? Yeah, exactly. You're going to be subtracting instead of adding. Or put it in your calculator as a negative. It would work the same. You can go negative 25 plus 273. Or go 273 minus 25. Either way, what are we going to get here? 248. That sounds about right. How about a negative 89 degrees Celsius, which was that temperature in Antarctica the video talked about? What would that be?
126.
184.
184? Yeah, I'm going to go with 184. That sounds about right. And then let's say you go to outer space. I don't know if you've seen the Marvel movies. What's the one with the weird guy that calls himself Star-Lord? Guardians of the Galaxy. Okay, so the second Guardians of the Galaxy movie, he goes out into outer space, and like the blue guy is saving him and puts his face mask on him, and the blue guy freezes to death. Because the temperature of outer space is like extremely cold, super cold. So what would the kelvins of outer space be? 273 and a negative 270. We're left with 3 Kelvin. Yeah, that is extremely cold. Now, not as cold as those places you saw in the video that are going to like nanokelvins. Outer space is incredibly hot compared to that, but compared to what we are used to here on this planet, yeah. Scientists without a spacesuit in outer space, they would freeze to death, amongst other nasty things that would happen. Yes, they would also, I wouldn't say explode, but it'd be bad. They would get super puffy, things would happen, bad stuff. So don't go to outer space without a spacesuit, please. Let's go backwards. Let's go from kelvins to Celsius. So instead of adding 273, we're going to subtract 273. So 500 kelvins is 227, sounds good. Oh, that's still quite warm. 300 kelvins minus 273. 27 degrees Celsius. That's like about room temperature. This room right now feels a little warmer than usual. It could be very close to 27 degrees in here. So we're about 300 Kelvin right here in the room. So colder than this room, 200 Kelvin would be what? Now remember my warning, we can go negative in Celsius We won't ever go negative in Kelvin. So do keep that in mind as you work. It's a great way to let you know if you added or subtracted incorrectly. So 100 degrees Celsius, wow, 100 degrees, 100 Kelvin, don't know why I'm having so much trouble with that. Negative 173 Celsius, super cold there. Okay. So simple math, and in just a few minutes when we're done with Dalton's law, we're going to get into Canvas, and that's all I'm going to ask you to do in the Canvas quiz. I'll give you a Kelvin, you give me a Celsius, or I'll give you a Celsius and you give me the Kelvin. And again, the equations are here on your chart. You get to use your notes on the practice and on the test in a couple weeks. So plan to use them and get super easy, good grades. We're going to finish up today's lesson with Dalton's law of partial pressures. So if you find that paper, guess who Dalton's law is named after? Yeah, shocking. Mr. Dalton, right? This is John Dalton, who actually even proved atoms existed last semester. So hopefully last semester you might remember we talked about atoms existing. How do we know they exist? What are they like? Same John Dalton. He did experiments with gases, and here's the thing. He proved when you combine gases in the same container, the pressure of them combined is as easy as the total of all the individual pressures. Now, I hope that makes sense, but let me point out, it did not have to work that way. We did not know that's what nature did until John Dalton proved it with his experiments. So I have this little illustration here I did not make, but I liked it a lot. If I take these 5 containers of gases and I squish them all into one container, then the pressure shown on the gauges here, now I didn't officially count all the little dashes to make sure, but if you add up all those little dashes, it should equal, all of it total should equal that one. That's Dalton's law of partial pressures. If you add up gases into the same container, you can just add up their pressures and there's your total pressure. So it makes it a super easy calculation. So here's the formula. Total pressures, pressure 1 plus pressure 2 plus pressure 3, et cetera, et cetera. Again, we did not know that nature did it this way until his experiments showed us, yeah, nature does it this way. So it turns out really nice. I want to remind you, we have been working with pressure. Pressure could be in atmospheres, could be in millimeters of mercury, could be in torr. Those are common units for pressure. Does it matter when you're adding them if they're in atmospheres or in millimeters of mercury or in torr? No. Here's the catch. Listen well. As long as they're all the same, it doesn't matter which one they're in, you just add them up. So as long as they're all atmospheres or all millimeters of mercury or all torr, you're okay to add them up. Now here's the good news. I'm not going to trick you and mix them up. So you don't have to worry about that, but that is something to just keep in mind. They have to add them up correctly. They have to be in the same label. Let's look at the back. I've got some example. Oh, before we get to the back, here we go. I got my car tire. Right now it has 18 PSIs in it, but I need it to have more than that because that's what's recommended by the manufacturer of my car. So I take my gas, my pressurized air tank that I have sitting in my garage full of air, and I add from my tank into my tire. So if I take 18 and I add 14, guess what I get? 32. It's that easy, you just add them up. Now I'm going to ask you these sometimes in a very tricky way. So flip to the back. Do you remember the lab we did where we caught the hydrogen gas in an upside down test tube, and then we put the burning splint into it and went whoosh? Okay. We did that and I lied to you. I told you that was pure hydrogen in that test tube. It wasn't. some of the water that was in the test tube evaporated as the hydrogen bubbled up. Well, if I'm doing gas laws, I don't want to do gas laws with evaporated water. I just want to know what the gas pressure is. So we'll use Dalton's law to get rid of the water vapor mathematically. So check out what we have here. Hydrogen gas collected over water. So I have a little picture of that, very similar to what we did. They're using a beaker. We used a test tube, same thing. If the total pressure is 825 and the evaporated water's pressure is 24, how much is the gas? What math are we going to end up doing this time? We're going to subtract. So pressure total is the pressure of the gas plus the pressure of the water vapor. So I'm going to have 825 torr equals x plus 24 torr. So as you just told me, I'm actually going to end up subtracting 24. So the pressure of my gas is 801 torr, I believe. Did I do that right? Okay. So Dalton's law is often used in a subtraction sense, not just an addition sense. And I will be asking you some subtraction type questions as you practice. So just read the question well. I like doing that thing where as I read, I circle the number with the label so I know what I'm working with, and you figure it out from there. Two more examples. Here is oxygen in the container, here's nitrogen in a container, and then I put them both in one container together. If oxygen is 159 millimeters of mercury and nitrogen is 593 millimeters of mercury, what's our total pressure? I heard 752. Okay, are we adding or subtracting? Adding, yeah, we're putting them together in the same container. Let's add them up. So if you would add 159 plus 593, I do feel like 752 sounds about right. Is that about right? Yeah, okay. One final example, because again, I want you able to add or subtract for these, depending on the situation. And I'll walk through those as you practice. I'll walk through those with you. So, 4 atmospheres is the total. If the pressure of gas A is 1 atmosphere, what must be the pressure of gas B? 3. Yeah, we had to subtract in this case to get the answer. There we go. 3. That's all I would ask of you on these as we practice. Add them up to a total or subtract them for a individual. Take whatever you're told, subtract from the total, get your individual. Okay, practice is in Canvas. Now there's lots going on that Canvas page. Students in the room, you already did, because you turned in to me your papers with the questions. Okay, I can't get a different color. But students in the room, you already did this. You don't have to worry about that. Students in the room, you already turned in those. Okay, we did the notes. Everyone, there's 2 practices in Canvas here. 2 practices, one short one over temperature, one short one over Dalton's law. Go ahead and get to work. We have about 25 minutes. I'm betting you could get them done before you leave, but if not, they're homework. Please let me know how I can help you with them. That's why I'm going to stay on Zoom and be listening if you have any questions about that. Go for it. Okay, so get just started on that. I'm listening and let me know how I can help you.